Now let's come back to frequencies and mode shapes and natural period. This is the diagram showing you what is the nature of the vibration. The thing is that this is a wave of the motion, and basically a circular frequency, circular angular frequency is being converted into a translational motion. And this relationship is the most hard for many people to understand, because when we solve the natural frequency, we are actually, frequency is a circular motion, but we're talking about moving of the body in translation. How are they related? This is how they are related. So the angular motion is related to translational motion through this relationship, right? Cos sine comes into play, and then that's how the angular frequency or angular motion can be converted into a translational motion or a wave pattern. So the frequency, which is angular concept, is then correlated with a translational wave motion. Okay. So this wave that you are saying, so this is pi by 2, pi 3 by pi. So every time it goes here, it starts from this one. And as you can see, this is the sine of the theta and so on, cos of the theta or horizontal, sine of the theta vertical. You just plot them together and you get this one, right? So this one cycle of the motion from here to here, one round of the circle is one, you can say, period, one natural period, one cycle. The time it takes to complete one cycle, we will call it, that is the natural period of a structure. And how many cycles are there in 1 second? Opposite of that will be the frequency, right? So frequency and natural period are now interrelated. One is the number of cycles per second, which is frequency, and one is the time it takes to complete one cycle, which is the natural period. So we use both. Mechanical people, other people mostly use frequency. Structural engineers mostly use natural period. We use both. I personally use natural period more than frequency, because it gives you a clear sense of the time. How long will it take for one cycle to be completed, or one complete motion of the structure this way and this way will be completed. I think this was shown by Mark on his presentation also. Okay, so this is how, so omega is the frequency, and it means this one, 2 pi seconds, one cycle. This is omega is equal to 1, omega is equal to 2, that means 2 cycles will be in 1 second. Omega is equal to 3, 3 cycles will be in 1 second, right? So the frequency, higher the frequency, smaller the natural period, because they're opposite, right? And the length will reduce, right? Amplitude doesn't change. Just the time scale becomes shorter. And this is the key to understanding everything. Now, look at the structure. So we are saying that the structure, let's say we say the structural natural period is 4 seconds, right? So which means in 4 seconds, it will go and it will come back to the same position, take 4 seconds. But also it depends on how far it goes and how far it comes back. So that means this displacement and the duration, both are important, because time is related to both the speed of movement and the distance it travels. So, which means that if we know the natural periods and frequencies properly, we can assess a lot of things about the tendency of the structure to move and how far it might move. Okay. So, with this knowledge, then we can see this is now, okay, so this is a mass which is 4 times the mass of that small mass. So now it starts to move first, then the second one will move, because this mass is higher mass. So that means the natural period, this is more flexible structure. It will move first. right? And then this for stiffness is 4 times, then this will, so now this is t is equal to 2. That means it will take 2 seconds to complete 1 cycle. And it is the softness of the structure because the spring is here. So the mass and stiffness interplay. So you increase the mass, the structure will become softer in terms of the motion, and it will be the easiest to move. And you increase the stiffness, it will become harder. So you have a mass into stiffness, and you can see there's a clear multiplier with the same thing, right? And this is another one. So this is the mass is the same, but the height is changing. Section is the same, but the stiffness will reduce now, because stiffness is not only section sizes, it's also the height. So which means that we can correlate now the mass and stiffness of the member and height of the member together. Stiffness means the section stiffness, and length is another part of the stiffness, K E over L. Okay, so now we have the same mass in all of them. And so you can see if this one is the natural frequency of that one, and if I excite this one, only one will move. That means the natural frequency of the structure is the one that will respond to a particular ground motion if the ground motion matches with that exactly. And if I move it slowly, only that will move, the other will not move. And if I do it very, very fast, then only this one should move, this one. So which means the frequency you can determine now from the way that you move the base, and that will tell you what is the natural. So if the ground motion matches the natural frequency, the structure will respond very, very strongly, right? So this is a very simple demonstration of the same thing here. So this is called molar structure. This is another device kind of thing. And this is, we can study the effect of fixed ends and number of stories and many things. We will do this a little bit later, torsional mode and this mode and that mode. You can study many things with this later, right? But the point is that the physical demonstration of these equations is very easy, right? And you can feel by yourself that if you apply this one and this one, and then this one, you will feel how much force you will need to apply to move them, to bring them into the natural frequency or natural motion. And that force, what we're talking about, stiffness and all. So you can experience all those things easily from these models. All right, so we'll come back to this next time. So if you have a multi-degree of freedom, not just many masses and the stiffness, so then that will move first, that will move later, and then that one will move last. And then the second bending will start. Now these different masses will start to move like this one, right? Not together. Now that is what we call the first mode, when all of them are moving together in the same way, like a cantilever. After that is done, then the higher modes will be that each mass will start to move independently. And that's what you see here. That is now they will move in one single curve, then double curve, then triple curve, and as many curves as there are masses, right? And each has a greater stiffness and greater stiffness and greater stiffness. Each is corresponding to, and each frequency will be higher, period will be smaller. So which means that the structures can continue to exhibit many, many modes of vibration. These are the modes. Each one is a solution to that eigenvalue problem, each shape. With a number, scaling factor is called the frequency, and the displacement pattern is the mode shape, right? Please watch carefully. So the first time it's moving like that, all of them are going simple cantilever, all masses moving together. This one also moving together. This is natural, we are not shaking it. And the next one after that, according to the stiffness, this is this most stiff, less stiff. So this has the most easy to go, most far to go. Then bending like this, one curve. Then this one curve. See? And then double curve. So each mass is independently moving. This is the tall building behavior, where each floor will try to move relative to each other in higher modes and higher modes and higher modes, right? So the structure can move in as many modes as there are stories. And in each direction, there are three directions: X direction, Y direction, and then torsion. It will also twist like this one. So the structure can twist, can move in X direction, Y direction, and each has its own particular frequency, particular shape, particular stiffness, which will be activated, particular mass that will be activated, right? So all of this, which means we can now study for the structure to start with, to understand what does the structure want to do. And if we know what the structure wants to do, we can either let it be, or we can say, no, I don't like the way that you're behaving. I want to change it. So you can come back and change the stiffness, or you can change the mass. And you can bring it exactly where you want it. So which means you have to have three things now. First of all, you have to be able to model the structure and determine these mode shapes and frequencies. Second one, you have to know what is it that you want the structure to be, what is good, what is bad. And number three, you have to know how to fix it. And that's your project. So the first step in your project should be to find the mode shapes, frequencies, natural periods of your structure. Check if they are what you want and they are acceptable or not. And if not, fix it, bring it to what it should be. 3 steps. All right. So now let's see what it should be and what it should not be. Okay, now let's look at a 30-story building and see how it will behave. So this is how it will behave. First mode, second mode, third mode. We are calling frequency 1, frequency 2, frequency time period 1, time period 2, time period 3. One more time so they can see it. So you can see here, this is a cantilever, one curvature, this is double curvature. It will continue to add more and more curves, give you higher mode and higher mode and higher mode, right? Like you saw the previous one. So which means we are looking for several modes of vibration in a building. And this is one direction. Building has 3 directions, at least primary. So let's go to the next one. So this is the second important observation. That is the ground, that is the total movement of the building for an earthquake. So if there's a ground motion, the building will move like this. Watch it carefully. This will randomly move somewhere here, somewhere there. Every mode is present here and being activated. So this motion is a summation of all the modes for the structure. You can go infinitely by adding all the modes. That means for a ground motion, because it has so many modes, the final shape of the movement will be summation of the modes that will be activated. So that means the structure's final response is not one mode, it's a combination of modes. And that will bring us to modal combination later when we discuss. So you can see, watch, this building is moving randomly, appears to be moving randomly, but it is nothing more than the summation of its natural modes in different order, different factors. So which means now we understand some important thing, that the natural modes will be very important when responding to external forces, like you see here, or external displacements. And those natural modes will combine together when they can. So we have to understand individual modes. We also have to understand their combination, and we have to understand which one will be activated, which one will be suppressed. So now in actual structures, we can suppress certain modes. How can we suppress certain modes that we don't like? We only want certain mode to be suppressed during motion. Dampers, devices like that, you put them there that only respond to certain modes and they become active, and they are not active for other frequencies, and they can come back and alter the structure. So dampers and those active, passive, so many damping devices can be used to suppress or even enhance certain modes, depending upon what you want. So that's the story about modes. So rest is text that you should read. Modal response, time period, and mode shapes are inherent properties of the structure, do not depend on applied loads. So this is the same statement that I made when we were studying the last class. What did I say? Same thing, that this is a natural property of the structure, does not depend on the load. What was that property? The interaction surface, when we develop the interaction surface of the column, and we say, okay, this interaction surface, the nice, beautiful color diagram of PMM is a property of the cross section, and it does not depend on any external loads. This only depends on the section definition material. So I said the same thing, and you forgot, all of you. Good for you. I'm saying again that the natural response is the property of the structure, does not depend on the load. Please go connect them together. Remember these things a little bit, right? Otherwise, what's the point? Okay. You cannot ask ChatGPT what you don't know. So please know the questions. Okay, all right. So there are as many modes as the degrees of freedom in a system. How many degrees of freedom are there in a structure? How many? Infinite, correct? How many degrees of freedom are we interested in a building? There are three movements in each direction, 1, 2, and rotation. So at least 30. Minimum 30 degrees of freedom of a tall building you should study as a floor level, because each floor can move X, Y, and rotate. 3 degrees of freedom per floor should be known by now to everyone. 7 degrees of freedom is for one particular node or a point of deformation. I'm talking about the whole building. Yes, 7 degrees of freedom if every degree of freedom is free to move independently. What for a building, normally all the columns are connected by the slab, so they will move together. Each column cannot move away. They're going to move together. So this is 1 degree of freedom per floor for X direction, 1 degree of freedom in Y direction, and the whole thing is rotating, just like I broke this one, exactly like that, right? So please remember and understand these basic concepts of degrees of freedom of a degree of freedom of a point, degree of freedom of a frame member, degree of freedom of a structure, of a building. They are different. So when you're doing the modal analysis, you should look for at least 10-story building. You should look for 30 numbers, because 30, I showed you just now 3, but it can be as many as the number of floors. We normally don't look for all of them, and I will tell you later. This one has 2 degrees. So this one also has 3 degrees of freedom, and we intentionally locked the other. So I only have this one left now, 1, because we want to study only that. But actually, it should move in that direction, but we locked it here. So this degree of freedom is locked. So you cannot, and torsion is still there. I can still twist it a little bit, but the stiffness, this stiffness is the smallest, so it will move in this direction first. And torsion is high, and this time is impossible, so it will never move. So which means that the structure will move in the weakest direction first. So first mode will always indicate the weakest direction of the structure and weakest tendency of the structure. So it's as simple as that. Next mode will indicate the next weakest number and direction, and so on and so forth, right? So not all modes are significant. This third statement is extremely important. Like you said, millions of degrees of freedom, but we are not concerned with millions of degrees of freedom. We are only concerned with the important ones. And for a building, I mentioned to you that even though there are millions of degrees of freedom, we are only interested in 30 out of that. or 10 out of that, or 12 out of that, which is called the significant modes. So you should know which one is significant and which one is junk, right? So which means this is very important. Locals mode may disrupt the modal mass participation. So there are local modes and there are global modes. So we have to ignore those small insignificant modes which might also show up sometimes. Okay? And I will show you what that means. Higher mode effects may significantly affect the dynamic response of tall buildings. This is very important, specifically a tall building. Other structures do not have this problem. But tall buildings have a problem with the higher modes. What does it mean, higher modes? High floor or what? Higher mode. Which is a higher, what do you mean higher mode? Higher mode means high frequency and less period. Those are very important in tall buildings. Okay, important points. Modal analysis should be run before applying loads. So which means, because modal analysis does not depend on the loads, so you must run it before you apply the loads. So you make the model, the first thing you do is run model and check what's happening. You don't need to apply dead load, you don't need to apply wind load, you don't need to apply live load. No load is needed. As soon as the model is complete, push model run and look at the structure and get all the things that modal analysis is useful even if full dynamic analysis is not performed. Many people think, oh, I'm not doing dynamic analysis, I don't need modal analysis, because modal is a dynamic analysis, right? Kind of. But that's not true. Modal analysis is useful even if you do not want to do any dynamic analysis later. If you just want to do code-based design or whatever, modal analysis is extremely important. That's why we have a whole lecture dedicated to that. And lastly, it's easy to run and fun to watch. You can see, you just saw the modal analysis results. Like, animations are good, if you like. So this is the modal results and output from ETABS. I will not go into too much detail. Like I said, this is how of the problem, which we will do later. But you can see that you can get many things from ETABS. And you need to understand each one of them, because when you run the modal analysis, you will get 7 or 6 or 8 different types of tables coming out from ETABS. You should know what they contain, how to use them. Because even though the first important thing is natural period or frequency and the mode shape, the vector of displacement, but then there are many things which are computed by the program from these 2 things. And those are very important informations. For example, mass participation. That means if the structure was moving, how much mass was moving in each mode? That is called mass participation. How much mass, in this case, 100% of the mass is participating because there's no other mass. But if you have a lot of mass everywhere, in the first mode, how much mass is participating, how much, so mass multiplied by displacement kind of a thing. How much mass got participated? Because maybe some mass at the bottom did not move at all. So that mass did not affect your modal response. Like the basement is below ground. The basement mass is not going to change your modal response, even though the mass is there, but it's not going to move. So it has no meaning. So having mass only is not important. Having mass that can move is important. And where it is, how much it will move is important. So all those numbers are given by modal direction factors, modal load participation factors, modal participation factors, modal periods and frequencies, modals participating mass ratios, response vector mode. So many things look the same. They seem the same, but we need to understand what they are. Okay? So when you do that, please make sure that when we talk about ETABS, we come back to this one, you understand and read more clearly what each of the output is telling you, because it's a lot and it's very, very useful. Mode shapes. So mode shapes, like I said, is the deformation corresponding with each vector, because degrees of freedom have vectors. If it's a 10-story building, it has 10 displacements associated with that. This is only one, but we have seen if they have 3, then there are 3 displacement can move. So those displacement vectors are mode shapes. And I already showed you that. So modal analysis can be used to do many things, symmetry of the structure and resonance and many things one by one. So I will show you all of these now, of course, on Friday. But you can use the modal analysis and mode shapes, natural period number 1 and mode shape number 2, and the distribution of modes and the I would say the stepping in the mode. I mean, honestly, if I want, I can spend the whole day today and tomorrow, 8 hours each day, only talking about the importance of modal analysis. Is so much data there. Okay. So I expect you to read something by yourself also. This is the key point, and this is your first thing for your project. Is model that please do not mix model with modal. Modal is AL, model is EL. Model is what you input, modal is the response that you will get. So the model that you make, is it trustworthy? Is your model good enough? Right? Did you make any mistakes in the model? That can be checked. One quick way to check that is check your modal results. And if your model results are okay, chances are your model is okay. If your model results are bad, then there are two possibilities. One is that your model is bad. Second is that your structure is bad. So which means that you model it correctly, but your model response is still bad. That means your structure needs to be fixed now. It can check for missing stiffness, missing mass, incorrect boundary condition, incorrect mass or stiffness units. This is the most common error people will make. Units of the mass or stiffness, mass especially. People choose the wrong mass unit because kilonewton versus ton is a 10 order difference, right? So if you choose the wrong unit, you can mess up the whole thing. E value is wrong. You mess up the E value by 10 easily. Can be done. People have done it. Most common mistakes, wrong E value. Stiffness is off by 10. Wrong mass off by 10, right? And people don't know what they're looking for. They think everything is okay. I know a case of a real building that the person entered the steel mass for concrete properties. So entire model is now based on steel mass. But they didn't check the modal response, calculate everything, do the foundation design, and foundations are so big and they cannot understand why the foundations are so big. Because everything seems like bending moments are nice, everything looks good because, it's just the mass is wrong by almost 10 or 5. And it went to the site, engineer didn't even, contractor said, no, I think for this building, the foundations look too big. I have done many buildings like this one. Doesn't look right to me. He complained to the client complained to the engineer. Engineer checked and found out that they made a mistake of the mass unit, mass number. Had they checked the natural period, this would not have happened. It's that easy. Okay. Connectivity errors, structural irregularities, symmetry, validation. All of this can be done if you look at the model response and if you know how to look for the things. So we will start now with the natural response. Now look at this building here. This is mode 1, mode 2, mode 3, mode 4. Same building, we will look at 4 modes. Mode 1 is moving in that direction. Mode 2. Okay, so that's the second mode. Then click the third mode. Now you see this one. So first it moved like this one, now that one, and then the next one, fourth mode. This one. So torsion, right? So now you can see that the building, this building has a little bit complex modes, not simple one. But you can see that every mode is different. Can you just rerun 2 and 3 at the same time? Okay. So now we have these modes running for this building. Okay. So which means that reading the modes is the most important thing to understand the building, what it is doing and why it is doing that and how to fix it. Okay, let's move on. Okay, now let's look at a symmetrical building now. That was not a symmetrical building, that's a random building that I took, right? Now let's look at intentionally a symmetrical building. So there's a frame building, completely symmetrical. So it must have in the both direction, not like this one, both direction, it must have almost exactly the same response, same natural period, same frequency, and same movement. So let's see. So now this is mode 1. So look at, yeah, voice. Mode 1 is 2.26 seconds, right? And mode 2 is also 2.26 seconds, exactly the same. That tells you that the building has been modeled perfectly symmetrically, and the program was able to calculate the modes exactly the same. And it could be any way, 1 or 2 could be switched, will not matter. X and Y in this case doesn't matter because both of them, so the program just picked randomly one of them. Circular building, perfectly circular building, you can never find which mode is first and second direction because it can move in any direction. All directions are equal. So basically it can move in any direction, right, at the same time. So all first modes will be exactly the same around. So the program has difficulty in finding the next mode because so many modes will be in the same frequency in every direction, right? So they have to check it, made a check that will not keep on giving you all the modes in the same. So after some time, they will put some tolerance and go to the next level and so on. Okay, so this is the third mode. First mode, second mode, and third mode. This is the behavior you would expect for a perfectly symmetrical building, X, one direction, two direction, and then torsion. That's the most common behavior for a symmetrical building. But sometimes a perfectly symmetrical building will have torsional mode as the first mode. And I will ask you later, how is that possible and why that happens? Perfectly symmetrical building, first mode is torsion. Okay. So now you can see it from the top also. So X direction movement, purely Y direction movement perfectly, and then rotation from the top. So that's how the buildings will move in 3 modes. And so when you're looking at the modes, always look from the top. So you can see what's happening to the building direction, right? And then you can see from here that, okay, this is the way typical symmetrical, perfectly symmetrical building, balanced stiffness should move. And now let's look at the series of these modes. So these are the all 4 modes in one direction. And this is where the key point is, that we are not looking at mode 1, 2, 3, 4, 5, 6, 7 around the building. We are always looking for also all the modes in one direction and all the modes in another direction and all the modes in torsion separated direct by direction. Because then we will understand much more. If you just look at the modes in that order, it's not useful. The important thing is to look at the modes in 1x, 2x, 3x, and 4x, and similarly 1y, 2y, 3y, and 4y, and then torsion 1t, 2t, and 3, 4, 4t. That will tell you a lot of things about the building. So much information is there. I will come back slowly, but this is the second thing you should look at, not only the order of the modes, but the modes in each direction as long as you can go. So typically we should look for 3, 4, 5 modes in each direction for a tall building, or sometimes even more when higher modes come into play. So that's, as you can see here, as a cantilever, single curvature, double curvature, and then quadruple curvature. Plan irregular. Now I put a wall here in this building. On one side, I put a wall. So when I put the wall on one side, what do you expect? Torsional weakness, because now the torsion will become the first mode, because now we have created a softness for the torsion. So modes always go for the soft side, not stiff side. So first mode means the least stiff building. So if you put a wall there, that means we have weakened the torsional stiffness of this building. And so on, we are expecting now that the first mode, if you do that, is this still in x direction, and now second mode is in torsion, and third mode is also torsion. Now, why the first mode did not go into torsion, we can talk about that later. All right, so anyway, so this is a very important lesson. When you make the building unsymmetrical, it is not necessary that the torsion mode will become automatically the first one. It will become either the first or the second. It depends also on because like I said, stiffness is governing. So if the stiffness of one mode is still weaker than torsional, then that mode will still be activated here. And the reason why this is happening is that if I go back, look at this one. This wall did not change the stiffness in this direction at all, but in this direction changed a lot. So this mode remained the weakest still. And then the other side became stronger, very strong, so the torsion became weaker in between. So it's the shifting of the stiffness that governs the order of the modes. And for earthquake, the torsional modes do not contribute to base shear. That's another important observation you should remember. Torsional mass is self-balancing. So it does not create a total force on the building, base shear, because the building is not moving, it's just twisting. So individual columns, individual footings will get a lot of force, but as a whole, the building will not get any net base shear. So torsional mode is very dangerous for local effects, whereas the primary modes are dangerous for the global effect. Okay, so that's that. Irregularity vertical. So what I did now is that put a short wall on one side, one long wall on one side, which means the building is no longer symmetrical in the same way. Okay, now this building is now vertically, so we have a wall on both sides and then one wall suddenly stops. So now vertically, this building will twist in a different way. Below it's symmetrical and upper it's unsymmetrical. So it has vertical irregularity also in some portion. So it should now have a complex mode. So vertical irregularity, this mode is this direction because both walls here, then this one, then this one. Okay, now this one, and you can see here, now the modes you cannot see much difference, but what you will see here is the vertical irregularity is now causing the twisting of the building in mode 2. So the effect of the higher modes, effect of the vertical irregularity, you cannot see in the first few modes. It will be apparent in the higher modes, okay? Because that's where the parts of the building start moving. Okay. Mode 4, see mode 4 now. And then now here, now you can see the effect of the wall irregularity. He's trying to create a dance move. Yeah, somebody should create some dance moves around this movement. Okay, so now you can see that the higher modes are becoming affected by the vertical irregularity. So that's lesson number 5 or 6 or whatever it is, that when we have vertical irregularity, higher modes will be affected, lower modes may not be affected. Okay. So that's the mode number, what's that? Mode number 9. So we went up to mode number 9 to look at the entire behavior. Okay, and we can observe that when did the higher modes be started affected by the vertical irregularity. Different stiffness along X and Y. This is another very important thing to watch out for. In this one now, what I did was we put 2 walls in one direction, balanced, but no stiffness. So the building is symmetrical in each direction, but stiffness is very different in the 2 directions. So this is not a good thing at all, because in one direction, the building is very strong. In one direction, building is very weak. So if there is a wind or earthquake on a diagonal side, this building response will be very bad, because building will heavily twist now, because the stiffness is so so different in each direction. So let's see what happens in this building. So mode 1 is weaker. Of course, we expect that. Mode 2 is in that direction. And mode 3 is in torsion. But still, the modes are correct. But look at the numbers. And that's where the problem is. It's not the modes anymore because building is symmetrical. So the modes will be like that. But the jump, you remember previous building 2.2, 2.2, 2. Like that. Now 2.2, next mode 1.4. Suddenly the stiffness is much higher in the other direction. That means the building will respond very differently in two directions. Base shear will be very different in two directions. Forces will be very different. Deflection will be very different. So we don't want that. Especially for inclined earthquake, this will behave very badly. So we try to keep the modal properties in the two directions similar. So symmetry alone is not enough. We also need a good order of the modes value, the frequency values. And then this one, 1.4, and then 1.1. So that's the next lesson about the modal properties. So all these things, every slide that I showed you is a check for you on your project to make sure that you do not have these problems. These are all indicating issues in the buildings. Next one, and probably the last one in this one, is that all modes are not equal or are not important. Because like I mentioned to you, that the program will calculate the modes based on the mathematics. It doesn't know what is the physical meaning of those modes. Only we know. So when we look at the modes, we need to only concentrate on modes that we are looking for. For example, if you are looking for the vibration in the floor, you may want to look at the local modes of the slab, which will be very high frequency. But if you look at if you try to do the analysis, like modal analysis, you will not even find those modes in the slab ever, because they are going to come after all the building modes are finished, maybe mode number 100 or 120, and you will not know, you will not find it. So if you want to look for a certain type of mode, you have to do analysis by locking other things out or looking for a certain range of frequency. So when you do the analysis in SAP or ETABS, you can find the frequency range that you're searching for. So it will only give you modes in that range. So we have to take out the frequency from the beginning, from the end of the range that we are not interested in, right? So that's the searching of the correct modes. So we can resolve the local modes often appear because of the disconnected members or something that we are not looking for. And I will show you one example. So global modes are those with higher participation. So global modes are the one in mass, more mass will be moving. Local modes will be the one with very small mass will be moving. For example, maybe one cantilever is moving. Maybe a building has a very large cantilever. So that might start moving before the building moves for earthquake. So that's a problem for the cantilever, but it's not going to have any modal participation for the earthquake. But that will still be something that you should worry about. So this is one example. So we put a small tower. Many buildings have such towers on the top, as you know, they try to extend it. So if you do a modal analysis with that tower in the model, you will find that that tower portion starts to move first, or the antenna starts to move first. And that will be your first mode. And you'll say, oh, this is not giving me any mass, because normally the first four modes should give you about 80–90% of the mass participation. But if you look at this mode, first mode, typically 50%, 40%, depending on the building height, should have a lot. Small building, 90% mode is first mode. But if you look at this one, this will only give you maybe 0.01% mass on the table. If you don't look at the diagram, don't look at the animation, you will say, what happened? My first mode is only giving me a mass participation of 0.001. It is because only that much mass is moving. The rest of the building is not moving in that mode. So which means that you have to ignore this mode and look for the next modes, frequency higher than this one. So that's important that you know what modes are you looking for, and you are able to fix the frequency range and then look at the mass participation factors. Okay, so now that we have seen many problems or many things. Now we can answer this question, is this structure good enough? Then we check the pulse. Like I said, you can now check the pulse. Check the pulse is natural period and mode shapes. You check both the things. And then you say, okay, everything checks out, is fine. Then you check the long period, flexible, mode drift, sudden jump in period, stiffness irregularity, unexpected torsion, plan irregularity, higher modes, are important in tall buildings. We need to do that and check for interstory drift and so many things. So this is what you do as your first step in your building design. This is the one that I was talking about. This is the type table that I expect you to make for your project, every one of you. Don't look at the modes randomly. Organize them in a matrix like this. So this is a very good way to understand everything about the building. So let's look at it. What do we have here? This is the translation in the weaker direction. All the modes you will put here. Then translation in the stronger direction, whichever that is, X or Y, and then the torsional modes in wind table. So this is the first mode in the minor direction with the longest period, 5.3, lowest frequency, highest mass participation, 60% mass is moving in this case. It's a 50-story building, so it's good. And in this direction, so we are looking at now mode, period, and mass at the same time. Next period in that direction is number 6, not number 4. So this is 1, 2, 3, 4. So they will not be arranged in the order anymore on a real building. They will depend on how they are activated. So this numbering is also very important. If it was a perfectly symmetrical building, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9. But in this building, that is not true. So it's going to be 1, and after that is number 6. That means some other thing got softer somewhere. So in this 6, now you can see is minor. And look at the jump from 5.3, it jumped to 1.28. That means the second minor mode is very stiff. This building has vertical irregularity somewhere. So it will, and look at the mass participation now is 18%. Drop. Total should be 100, about, for all the modes, 95, 90%. Now jump to the next mode is T9, 6.5%. And again, the natural period jumped a lot. In the major direction, in the stronger direction, the first period is 4.96, close to that one, not bad, because that means the stiffness in the two direction is similar. It's not much different because the period is similar, not big jump. And then number 4 is 1.56, big drop from there, 15%, 18%, 15%, 60%, 66%. And then mode 3, 4 seconds. So this range is 5, 4, and 4, good order. This one is 1.2, 1.56, and 1.30. So they are in the same order. And these were all in 0.75, 0.81, 0.65. So you can see the big jump in the period from 5 to 1 2 points, right? This is a typical things that you expect in a tall building to happen. Percentages is the percentage of mass participating in that mode. So in this case, 100% mass is moving because there's only one mass. But if there are many masses here, then in that mode, not all the mass is moving. Some mass is close to the base, is not moving. So which means, or some mass is not moving in X, it's not going to move in much X direction, will move in Y direction, right? So that is the mass participation ratio. We must check this one. And for earthquake analysis, the sum of all the modes mass participation should be equal to 100 ideally. But we normally accept up to 90% is enough. So if there is a mass below the basement, it will never move. So if you include that in the building, you will never get 100% or even 90%. So a lot of engineers make the mistake of including the mass of the building below basement, 7 basements, and they don't know why they are never getting 90% mass participation, because big mass in the basement is not moving, foundation is not moving. So we have to make sure that in the model, we set that mass to be 0 in the analysis. How do we use? You change the density of the material. You apply a different material over there and set the density to be nearly 0. So the mass can be 0. So this is the table that you need to understand about everything about the building. So you have to look at the percentage mass participation, the order of the magnitude, the order of the numbering, the difference between 3 modes in each row, horizontal. So normally 9, sometimes 12 more rows can be added, more columns can be added. So you should look into that. Very tall building, you need more. Okay, until you get 90. So here you can see here, in each direction, you should get 100%, not total. So this direction, now we have 60% here. We have another 20%, it's about 80%. And so it's about 84%. So that means we need more modes in this direction before we get the full mass. So in each direction, and in this one, in torsion, 0. Torsional modes do not count for mass participation because, as I mentioned to you, it's just twisting. So that's the story of the modal analysis. The modal analysis can also be used for many other things. For example, design of the mass, the base isolation tuning, tune mass dampers, damage detection, monitoring, wind engineering. Everything depends on modal analysis. Without that, there's nothing you can do. Especially advanced systems, all depend. Like I said, you're young people, you don't go to the hospital. Every time we go, first thing is say, go check your pulse before I send you to any doctor. So it doesn't matter what your weakness or problem is. The first thing is heart rate, right? Same thing. Any analysis you want to do, anything you want to do with the building, first information is look at the model results before you go to any specialist. Okay, damping. We talked about a little bit the other day. Let's go into a little bit more details of the damping now. So let's look at the big equilibrium picture first. What are we doing here? We are now moving this all the way. This is the 1, 2, 3, 4, 5, 6 forms of the equation that we are talking about. And this picture is very clear, telling you exactly what's happening to the structure. First one is, we are saying an idealized body, spring, is pushed by a force and is resisted by stiffness. Please look at the sentence. You should be able to explain the equation in a sentence. And I can assure you this will be in your exams. Equation, explain what is in the equation. Okay? Because if we can't explain what the equation is saying, we don't understand the physical meaning. Okay, so second one is saying that the body is in free state without any force, vibrating naturally, undamped in self-equilibrium. That's what this equation is saying. There's no force, but it's still moving. It's in self-equilibrium because there's no force. And it's naturally moving, undamped. Next one is saying an elastic body is being pushed by a time-varying force, is in dynamic equilibrium at all time instances. So the building is moving constantly, but at every time it is still in equilibrium. That's what it says. It's not running away like a car, not driving away. It is still in equilibrium at every time step, but it's constantly moving because the force is moving with time. Next line is saying that the ground is shaking, so the building is in constant movement, but in equilibrium at every time step, but because of the ground shaking. Next one is saying that the body is inelastic, being pushed by an external force which is varying with time, but there's a damage and building is cracking and it is breaking up while it's moving, but still equilibrium. And then last one is saying it's a ground motion, building is moving by ground, it's breaking up and it's damaging, but still equilibrium. So these are the stages of the structural response. Covers almost everything. Vibrating machinery, people walking, dancing floors, all is covered here. That is the FT. Like this one. See, everything is moving. I just vibrate the floor. So that's the FT acting on that. Okay, so impact, blast, everything is here. All kinds of analysis all kind of forces, all kind of issues, wind, whatever you need is here. So these equations you need to understand. And now what is common in these equations is damping starting from here. So this one doesn't need damping because it's idealized. This body is not real. So it's a spring. This one is natural, undamped, so it doesn't need damping, but everything else needs damping. So now the question is, what is damping? And it's multiplied by velocity, and it's a force. So damping multiplied by velocity is a force component generated by the body itself. So now let's look at damping in a little bit more detail. So damping, this portion here, is a velocity proportional energy dissipation. That's what we call it. It's an energy dissipation, which is velocity controlled. Motorcycles, old style, old especially, they have these shock absorbers in the front and the back, right? And if you watch them carefully, then that shock absorber is a damper. That's pure damping attached to a moving vehicle because of the ground is varying and the mass is, so there's an acceleration it's going to damp. Otherwise, you will be jumping around too much on the motorcycle. To make your ride smooth, that energy coming from the road because of your mass moving up and down is all being absorbed by that damper, or now so many kinds of dampers are there. But that is exactly what this is. So building has this built-in shock absorber in there, which is dissipating energy, and it is related to the velocity of the movement of the body. So basically, this is going to dissipate energy over time. So it's going to over time because velocity is time related. So over time, it will dissipate energy that is coming in. And causing oscillations to decay. Second part is most important in our understanding, because like I told you, this one is just going to go on. But this one stops more quickly because this has damping in it. This doesn't have damping in it. So the damping is the property that will cause this oscillation to slowly decay. Frequency will not change, the amplitude will change and will just become smaller, smaller, smaller until it stops. So damping is the one that's going to do that. It's no longer free vibration now when damping comes in. Without damping, structure will oscillate indefinitely, but in reality, all vibrations do stop. So that means damping is active. So physical sources, internal material friction, as I mentioned to you, this is micro cracking inside the body where you can't even see it. Friction, connections, joints, interface. If the body has connections somewhere, steel connections, they will have friction there. That friction, in fact, friction pendulums or friction dampers are very important, very useful. Opening, closing of micro cracks in concrete, radiation of energy in foundation and soil, and interaction with non-structural elements. This is very important. Last one is very important. We don't realize it. When the structure is built against partition walls, there's a small gap there. So normally we ignore partition walls and ceilings and other things. But when the structure moves, the walls also get connected and damaged. So they also provide a lot of damping. Even furniture, even the ceilings. So this is what is going to happen. That is the free vibration. Okay, so that is the free vibration and natural period time t between peaks, right? So this is going to go like this forever. But if you have damping, it will go down like this one, and at one point it will stop at some point. So this is what the damping is doing. Damping will bring this oscillation, amplitude, displacement down, frequency will not change. The period does not change on this one. Period changes because of the stiffness change, not because of damping. But the oscillation, the displacement changes because of the damping here. So more damping, this gold line will become narrower, right? And no damping, it will go to that is zero damping. So that is the equation for the damping. So this is the equation for damped vibration here. Okay, This is another view of the same thing. So now if you look at this oscillation, this one is this gray line is zero damping. This is damping, different damping, 1%, 2%, 5%, 10%, 20%. I'll tell you what is this percentage. So this damping ratio is the key because there's a critical damping, which I think you know, but we will talk about. So 0 is undamped, 1%, then 2%, 5%, 10%, 20%, 100% is the critical. So if 100%, that dotted line, it will just die out. Look at the important thing here. It will just die out in one cycle. So critical damping means that if the building or the vibrating stops after one cycle, it has critical damping, that it will only complete one cycle and then die. So 5% damping roughly means 20 cycles, roughly, not exactly, but roughly, and so on. So you can see here that it comes down, down, and this is like 10% here, yellow. It's almost becoming zero after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 10 cycles, right? Roughly. Okay, so now you see 0%, 5%, 100%, and that one lightly damped, different views. And this is the frequency, critical damping, and damping ratio, the equations for that. So natural frequency, critical damping, and damping ratio. I will have better equations. I just didn't replace here, just typed. Anyway, so natural frequency we already know. And then we also know critical damping with that formula, and then damping ratio. So these three things are very important for us to do the analysis. We need to know the damping ratio, which we almost never know. We assume something, and it is very sensitive. The analysis is sensitive to critical damping, the damping ratio, because the equation includes that. So if you choose the wrong assumption for the damping ratio, your results will be off, just like stiffness will be off. Okay, so where does the 5% damping comes that the codes use? Like you were asking, why do we need 5%? So 0 is this one, lightly damped, 2% oscillates and decays slowly, 50% amplitude drops up to 5 to 6 cycles, typical of steel buildings. And this is the number we use for steel buildings. We also use 2% for concrete buildings if we are using performance-based design for service level evaluation, where we are assuming the building has not been damaged at all. So there are different rules for code-based design and performance-based design. 5% moderately damped, standard codes assume oscillates but decays noticeably, 50% drop in 2 to 3 cycles, cracked RC. 100% is, of course, completely damped. So this is just a more explanation of why these dampings are used in practice. So damping, this energy dissipation. So please remember this equation at the top. This is very important equation, energy balance, because ultimately it's all about energy and energy balance. Okay, so this is so input energy, which is coming from force or earthquake, will be just like force inside the structure. You apply a force, inside there's mass and acceleration, there is damping and velocity, there is stiffness and displacement. Energy is doing the same thing. Each component of that equation is related to one energy component. So kinetic energy, strain energy, damping energy, and hysteretic energy. Nonlinearity, damping, elastic deformation, and motion for acceleration. So all 4 components of the equation are giving you each one energy component that will be ultimately balanced. So this is, in fact, everything is coming back from energy balance. Structure is going to balance based on energy. It's going to be an energy balance structure. And energy will dissipate, distribute, and that will cause all the things that are happening. So we need to look at, that's why in nonlinear analysis, in performance-based design, we always look at the energy dissipation plot, share of energy dissipation. So we have the kinematic energy, and then a strain, and the damping and the okay. So damping further has 3 parts: viscous damping, hysteretic damping, and equivalent viscous damping. So that means hysteretic damping is when you have cyclic degradation and it it changes, it keeps, the structure is going back and forth, cracking and something. So you accumulate energy in that loop. So that is steritic damping. And then viscous damping is coming from the material itself, friction, radiation, and so on. And then equivalent damping, which we convert that into applying the total damping. So damping is a very deep subject. Strain is just elastic strain, not hysteretic. You just bend something, it already has a damping because the material is just being compressed. So just you take the strain diagram, for example, and so area of the strain, stress strain divided by half will be the strain energy. Not about the damage, not about the loop. Hysteretic is when you complete one loop. So we have the various types of structural analysis: viscous, which is velocity proportional, Rayleigh damping, hysteretic, and Coulomb. These are different names of damping that you will see in SAP or ETABS. So you should know what do they mean. And sometimes we can give individual values for each damping, but generally we don't do that. We just give a global 5% damping, takes care of everything. But really speaking, each damping can be specified individually also in advanced programs. Nonlinear dynamic analysis, you can specify each one separately. And then you can model the dampers, you can model isolators, you can model whatever, like this one. So the provision is there to separate, but normally we lump everything together for the code-based design and say, oh, 5% damping is the total damping. All right, that's once again steel structure, welded, bolted, more reinforced concrete, uncracked, cracked. So you can see here, uncracked is about 2%, same as steel. After cracking, it may go to 5%. Pre-stressed concrete, now somebody asked the question, if you want to know that, this is the damping for pre-stressed concrete. This is for composite, you have the damping, that one. So we have the damping for that, but normally people just don't care to use that kind of level of detail. So this is the complete table that you can have for reference. And dampers, you can get up to 20%. Very, very large damping can be added, right? Just make the whole structure damped. Okay, Eagle Eye. So in Eagle Eye, watch this one. This is coming from Eagle Eye, one of the app that Dr. Fawad added to the program, where you can actually study all of this damping and natural frequency and the animations and change the numbers and play around with it like a small lab. So this is a dynamics lab, virtual lab. So let's see. Anyway, so basically you can change any parameters. If you go back here, can I go back? So this is free vibration, harmonic vibration, impulse vibration, periodic vibration, earthquake vibration, and arbitrary vibration. All kinds of vibrations with damping and without damping are covered in this app. So you can study them by entering the data, changing stiffness, changing mass, changing damping, and you can see the plots and the animations at the same time. So this is like a full dynamics mini course for you to try. Okay, it's like this is a physical lab, that's a virtual lab. Same thing. All right. So you can see that the output response parameters, modal properties, everything. And then you can change here, for example, mass, stiffness, lateral stiffness, column stiffness, damping parameters, excitation parameters, simulation settings, start time, end time, like this. So you can really play a lot of things here. This is probably one of the few apps that will let you do this kind of study on dynamics.